All right, welcome back to the counting slides. Let's keep on moving down towards here. So I am going to start with a question today, and this one is going to be about multiset. So let's remember the formulas here, what we're doing with our binary strings. But here's, after pausing and remembering, here's your question. So give this a try. We've got a bunch of coins right now. A bunch of coins are divided into 4 piles, and we've got pennies, nickels, dimes, and quarters in the pile. No 50-cent pieces or anything like that. So, first question, how many ways are there to select 25 coins from the piles? Let's say that you can get as much as you need, right? You have infinitely many coins in each pile, at least 25 of each. Okay, so how many ways are there to select that many from the piles? And then here's a follow-up question. So, the first answer is going to help. How many ways are there to select 25 coins if at least 5 of them must be quarters? All right? If at least 5 must be quarters, what does that tell you about what you need to be counting? All right? And then also remember that all coins of the same type, just like the puppies from the previous example, are indistinguishable. There's no difference. There's no first quarter, second quarter, anything like that. It's just a quarter. Okay? So give that a try. And let me get ready to show you my idea. I'll think about it. So it is a multi-set counting problem, so we're going to use the stuff that we talked about before, this formula. Let's think about it. So how many ways are there to select 25 coins from the piles? It's just like, all right, I want, like, order them, pennies, nickels, dimes, or quarters. You're drawing essentially 25 ones, and like zeros tell you when you're done taking a certain category. So like 3 pennies, put a 0. I would like to put and take 4 nickels, put a 0. I want to put 5 dimes, put a 0, and you put as many ones as you need to add up to 25 for the quarters, right? So that's pretty much what you're doing. You're counting binary strings, and we're counting them like a multi-set. So what do we got? What is our n and m, right? N objects from m varieties. We have 25 objects we'd like to select. And how many varieties do we have? M, that's 4, okay? So we're building how big of a string are we building? We're building a 25 plus 4 minus 1 sized string. And then what are we choosing out of them? We're choosing the places to put those 3 zeros, right? So it's m minus 1, right? Maybe I should write this first. The formula was, right, n plus m minus 1, choose m minus 1. And for our case, that's going to be 25 plus 4 minus 1, that's 28. We've got 28 ones and zeros, and we're choosing where we put the 3 zeros. Okay, so that's going to be the answer there if you want to do that math. And then the next question is, how many ways are there to select the coins if at least 5 must be quarters? Well, it's kind of similar to our other product rule incantations. It's like, well, the second you've picked 5 quarters, like, there's only 20 coins left, right? And how many ways are there to select 5 quarters? There's only one way if they're indistinguishable, right? So it's kind of like 1 times ways to select. Now it's 20 coins from the piles, because you've kind of forced your hand on the quarters. You can have more than 5 quarters, but at least 5 coins from the piles. So it's like a smaller problem, almost. And this 1 comes from the fact that there's only one way to pick 5 quarters. You just like go into the bag, pick 5 of them, because they're indistinguishable. Only one way to pick 5 quarters. Okay, so, all right, what's this one now? Now it's a size 23, I guess. Set of things. N is now 20. N plus m minus 1 is now 20 plus 4. Minus 1, choose, still 4 minus 1, yeah. So that's 23, choose 3. So you have less options, right? Because you're forcing your hand to get 5 quarters. Okay, I hope that makes sense. This 1 is important here. It's only one way to pick 5 quarters if they're indistinguishable, like we're assuming. Okay? All right, next idea, let's talk about sets, all right? We know, like, unions, but let's talk about sizes of unions. So if you take the union of 2 sets, if they don't overlap at least, like what's the cardinality, how big is that combined set after you take the union, you just add up the individual sizes. It's like when the sets do not overlap, like here's S1, it's like got all of its stuff, and here's S2 completely separate, no overlapping. like their union, of course, is the whole thing, and their size is just the sum of the individual sizes. But what if it's not that easy? What if there's overlap, right? There are some issues there, and like there's a whole field of study. It's called the principle of inclusion-exclusion, is how you count the size of a union when there is potentially overlap. So like S1, S2, if they look like this, the traditional Venn diagram, like they have some things that you share. You can't just add them up, because you've overcounted, right, the spot in between, and that's the problem. So the principle of inclusion-exclusion is the fancy word that tells you how to do this. So if there's just two sets, call them A and B, this is how you count how big the union's going to end up. So A union B, the size of that is the size of A plus the size of B. But the second you do that, right, you've double counted this middle bit. So what you do, the middle bit is their intersection. You double counted it, so you got to get rid of one copy of it. So that's why the subtraction is happening there. So here's A, here's B. Let's spell that out. So if this is A, like maybe A has, I don't know, 6 elements. 1, 2, 3, 4, 5, 6, and then 2 are shared. And then B has, let's say, 5 elements, right? So 2 are still shared. Notice how the total size is not 6 plus 5. That's too many, right? But you can get there most of the way. So the size of A union B, what's that? It's going to be the size of A plus the size of B minus the size of their intersection, because the second you add up their individual sizes, like you counted the 6 and you counted the 5, you counted these two twice, so you have to subtract one copy of those two, right? Because you don't only want to count it once. So that's what's going on, and this will give you the correct number, which is apparently 9. Okay. It gets worse. It gets worse when there's more sets being unioned and they all have things that can potentially overlap. So here's the idea for A union, B union, C. Here's A. Here's B, there might be some overlap, and then here's C, there might be some overlap with pairs of 2, see that, those edges? And there also might be an overlap with pairs of 3, and so now there's going to be like subtraction and addition as well. So like you'll add up the individual sizes, this is like the formula, you'll add up the individual sizes, and so that means you double counted these places where there's only 2 things overlapping. You double counted those, you gotta subtract those intersections. And then by subtracting those intersections, you like got rid of too many of the inner bit, because you counted that 3 times, then you like got rid of it 3 times, you gotta add it back in. It's disgusting. So you add in the innermost, their entire intersection, this bit. You gotta add that back with a plus, not a minus anymore. Like this took out too much, you gotta add it back in. So there is a formula, there's a pattern. For larger sets, the book will tell you that pattern. All I really care about is you understanding it up to here. You can follow the formula if you need to. You can derive it if absolutely necessary. So that's as much as I want you to know about it. Let's next talk about permutations and combinations. This will be a fun one. We'd like to generate these in code. So the way that we're going to generate them is in lexicographic order, because that's like an order that we can have and hold. So lexicographic order, that's just a fancy way of saying dictionary order. So like strings in C++, for example, are compared using dictionary order, lexicographic order. Like ABC will be less than BCD. That will be true for C++. This is also true, right? Because you look at the characters like, when will this come in the dictionary? A and A, B and B. All right, got to look at the next character. But the C and the D tell you, oh yeah, the C is less. So that's going to be a smaller thing. But it's like ASCII order. Like there's numbers. You can compare apparently the percent sign. That's smaller than the character for the open paren. You have to look out for that kind of stuff. But at least with words, it makes sense. So there are some fancy algorithms that generate every possible permutation of a set, and then every possible combination of a set in this fancy order, and that's how it knows when it's done. So this is going to be a topic of a future lab for you. So it's important to understand. We're just going to read off the code from the book, but it's going to take a while. It's kind of weird to implement it. Like all these words, they turn into code in a weird way, and they function in a weird way. So here's the algorithm from your book to generate every permutation of a set in lexicographic order. All right. And we're going to assume that our set is, like, we give it the input size n, so we're just going to say how big our set is. And you can always map each element of your original set to a number, so this is fine. What this function is going to do is going to generate every permutation, all perms of the set 1 through n. 1, 2, 3, all the way to n. Okay, so that's what this function is going to give back to you. And this one makes a lot of sense. It's like, all right, here's the first permutation in lexicographic ordering, like it's increasing from 1 to n, like that's the first one. And it's like, all right, print that one. And then while it's not equal to the last one, right? Because you don't want to go after the last one. That's when it's in completely reverse order. That's like the biggest one. That's like ABC is the start, and then you go to like ZYX. See that? Like this is the first one of permutation of all the letters. This is the last one. It's kind of the same for numbers. There we go. And so like, while it's not that one, just like, all right, let the permutation be the next one after that one. This function is the fancy one that's going to generate the next one in order. And then, all right, output that one. And so like this loop naturally will output every possible permutation if next perm does its job right. And gives you back the next one in lexicographic order, ending on this one, of course. That's the very last one. All right, this is the very weird one. We have to figure out why in the world this one's going to work. It's like, all right, we have to find some indices, like KB, the largest index. So stare at this for a second. Definitely go through the examples in the book. Very helpful. It's going to be like, it's going to find one index, it's going to find another index that has to deal with that first index. Then you're going to swap things and reverse things. And like, that's your next permutation. All right, so the only way truly to understand this is to do examples. So let's do some examples of next perm. Let's assume that n is 5, so we're calculating permutations of the numbers from 1 to 5. So like the function will start, this one at least, it's going to start with the numbers 1 to 5 in order. So like this is the very first permutation. 1, 2, 3, 4, 5, and like these have indices, like this is index 0, 1, 2, 3, and 4, like if you put this in a list or a vector. And then we want to feed this into next perm, right? Because that's the first one. We want the next one after that one, right? So we call it on that permutation. So those numbers, 1 through 5 in order. What does it do? What does it do on them? Let's figure this out, okay? So all right, it's going to find k. Let k be the largest index such that pk, so this is like the element at that index. Let k be the largest index such that the element there is strictly smaller than the one right after it, k plus 1. See that? So go and look at every index like this and see, like, is it true that the one on the left is less than the one on the right? This is true for all of these, right? It's like, all right, it's true for these guys. Oh no. Here, let's put it down here so I can move it. It's like, yeah, it's true for these guys, right? 1's less than 2, 2's less than 3, 3's less than 4. It'll just keep advancing. It's finding the biggest one, and 4 less than 5 is true still, right? So it looks like index 3, the one where 4 is the largest one, such that this is true, right? See that these are like that. So index 3 is our k. This is our element pk. Does that make sense? Because this is the index, right? This place is the largest one where the thing after it is still bigger than it. So like that's as big as you could go. It's the largest one it could possibly be. So that's good for us. If there isn't one, actually, that means you're at the end, like because everybody's like it's in reverse order. But we're going to assume we're not there. And then we're going to find index j. Let j be the largest index such that the value at that place is greater. All right, we want the thing furthest to the right, not the biggest number, but the furthest thing to the right that's still bigger than the element at index k. It's like, here's index k thing, it's 4. So go and find things, go and find the largest thing, right? Go and find the largest index that's bigger than 4, all right? And so like, it's only this one, right? 5 is the only thing bigger than 4, and that is the largest index, right? It's the only index where it exists. So that's index 4, and so that's going to be our j. And this will be the element pj, all right? You see how that matches? So j is the largest index such that p of j is bigger than p of k. So like this, look at 4. The only thing's bigger than 4 is 5, and so this is your only option of the index that's bigger than 4. And we've naturally found the largest one, the largest and the only one for this purpose, for this start. Okay, so that's pk, pj. And then what you do is you swap them. You swap them, and then you reverse the order of anything that comes after pk. pk plus 1 through pn. So let me show that to you. So like this is going to transform into, we're going to swap these bad boys, the 4 and the 5. This is going to turn into 1, 2, 3, 5, 4. And then we're going to reverse the order of everything after k. K plus 1 through n. So everything after that index k is, well now it's here, right? Like from everything from then onwards, reverse it. There's only one thing that's already in the right order. So this is the next lexicographic ordering of permutations. And so this is what next perm would give back for the first one. Okay? Hope that makes sense. So that's the start. Okay, we're getting there. So let's do it again. Let's say, all right, we output this one now. It's like we output it, and we come back to the loop. Oops, I did not mean to leave a comment. We're back to the loop, and then we say p equals next perm again. All right, so now we're looking at this permutation. Oops. We're looking at this guy. We're trying to see which one comes after that. So again, we're going to play the game of, all right, let k be the largest index such that pk is strictly smaller than the thing after it. So like, this is true, 3 is less than 5. 5 is not less than 4 though, so that means 3. This is the index. There's my pk. See that? It's an earlier index. Now that's a 3, by the way. This does not look like a 3, does it? There, so that's my pk for this iteration, for this version of next perm. Then we go and find j. Let j be the largest thing, largest index, right? The rightmost thing, the largest, yeah, let's say the rightmost thing, because that's what largest index means. Find the rightmost thing that's bigger than the thing at pk. So rightmost thing that's bigger than 3. I got 5 and I got 4, but I want the rightmost one. So I'm going to pick the 4. That's my pj. Okay? And so then what I do is I swap them. And then I do some things before I return the next permutation. So let's do it in green over here, scratch work. I'm going to swap the 3 and the 4. So I turn this into 1, 2, 4, 5, 3. Okay? And then remember where p of k was. It's still this index. We're still talking about this index. That's still index k, right? That third thing. What we do is we reverse the order of everything that came after index k. So these guys. This was index k, right? So the third thing. So this is the thing at index k now. I'm going to swap everything, or I'm going to reverse everything after it. So the 5, 3 will turn into 3, 5. Okay? So this will turn into 1, 2, 4, 3, 5. And that's going to be the next smaller permutation. That's the one that we're going to give back, all right? So this is what we're transforming this guy into. This is what next perm will return. Return what we just did. It's going to be 1, 2, this guy. 4, 3, 5. That was our scratch work on the right. Those are equal. Okay? And so I think you can, I highly encourage you to play around. Keep going. Like, see what the next one after this one's going to be. But do you see how this is like lexicographic order? This is like A, B, C, D, E. This is A, B, C, E, D, I guess. Yeah? Does that make sense? Like, naturally this one is after that one, and then this one comes after this one. It's like it's getting as small as possible. Like, this is the next bigger thing after this one. 1, 2, 3, 5, 4. 1, 2, 4, 3, 5. Like, it's got to be like, we're going to make this something bigger. And then what's the smallest thing I could put over here? It's going to be 3, 5, not 5, 3. That's why we did the swapping, right? So I hope that's starting to make a little bit of sense, but that's the algorithm. All right, I want you to think about that, and I want you to try it. So here, let's consider that we're trying to permute the numbers 1 through 7. So n was 7. And let's say we're at this permutation. We're at 5, 4, 7, 6, 3, 2, 1. So we're trying to permute these numbers. What's the next largest permutation for this one? All right, so your goal now is to take this permutation, write it down, and run this algorithm on it. Run next perm on it. Okay? What are you going to do? All right, so give that a try. And what do we got to do now? So we want to find the first index. Let k be the largest index such that it is smaller than the thing right next to it. So like, consider these guys. What's the order? Is the thing on the left smaller than the thing on the right? No. 4 and 7? That's good. 7 and 6? Nope. 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 Looks like it's only 4 and 7 is the only option. So 4 then. That's my pk. See that? There's pk. K is supposed to be a subscript. There we go. And then we find j, right? We want to find the largest index of the rightmost thing that is still bigger than the thing at index k. So 4, where are all the things bigger than 4? I got 5, I got these guys. I want the rightmost thing that's bigger than 4. It's the next place I want to look. So it looks like it's the 6, right? That's the rightmost thing that's bigger than 4. Largest index, so that's pj. And then what do? We swap them, right? So we're going to swap them. So we're going to turn this into 5, 6, 7, 4, 3, 2, 1. And then we have to do some reversing, right? So we take everything after index k, k plus 1 through n, those indices. So this was index k, right? This one right here. So everything after were all of these. So I'm going to reverse them. And you kind of notice, like, you know you're doing it right when this is in reverse order. Like, you want to be in ascending order because that's going to be the next smaller thing. this will get turned into 5, 6, 1, 2, 3, 4, 7. And that's going to be the next permutation. All right. I hope you're getting some practice with that and it's making a little bit more sense, but this is what you're going to program. All right. Do you kind of see how you go looking for these things? You'll have to loop. You have to do some loops. So yeah, that's that one. That's all I can pretty much tell you about generating permutations. Let's next talk about generating every combination, right? Because order doesn't matter for combinations. We're generating subsets. So let's generate all the combinations also in lexicographic order. Right, so this one takes two parameters, gen lex subsets R and N. So what this does is, it depends on the size of subset you want. So it's going to generate and give back to you all the subsets of size R from the set 1 through N. All right. So if you wanted to generate combinations of like words or doubles or something that's not the numbers 1 through N, other numbers maybe, all you have to do is assign a number to those and just like use that number, figure out where it's going to be. That's all. All right, that's something we're going to do in our lab. So yeah, that's supposed to do that. And so yeah, this one again makes a lot of sense. It's like, all right, the very first subset is like 1 through R because that's as big as it's going to be. So like if I'm generating all the subsets of size 5, I'll generate the subset from 1 to 5. That's the first one in lexicographic order. All right, and then we're going to try to never duplicate this. All right, so output that, and then the last lexicographic ordering of subset is going to be n minus r plus 1, right? Because we're going to try and keep this in some sort of order, all the way to n, those numbers. Okay, that's the last one. So as long as it's not that one, generate the next one, given our n and given our current subset, and then output that one. So this loop again makes a whole lot of sense, and this one is again disgusting. Okay, so let's figure it out together. This is next subset. So given size n, it's as big as the set is, right? That's the stuff we're taking numbers from. And this is my current lexicographic ordering subset. Again, I'm looking for an index. Let k be the largest index such that sk is less than this number now. All right, so that's an interesting special number. We'll see that in an example. And then if there isn't a k that works out, then that was the last one. So we shouldn't have even been called. But otherwise, I'm going to take the thing at index k, increment it, and then for everything after, right, for every index after k, from k plus 1 to r, that's the biggest one, right, all the way to r, also increment everything there. Increment everything after that. So it's like everything, honestly, from, oh, sorry. No, it's not an increment, excuse me. It's an increment, but I'm moving indices as well. Got to pay attention. So like take that thing, increment it, and then for every other index, you're going to shift things. You're going to take, all right, the thing at index j is going to be the thing from before, the thing at the previous index, plus 1, and that's just going to generate in ascending order for you. And so I'll show you that. All right. So that's going to be how you give back the next subset in a certain ordering. Okay. So you can also represent this as like a vector or something because you want to keep in order. So, all right, let's figure this out. Let's do the next subset for r equals 3, n equals 5. All right, so what is all this going to do? So like for the first one, this first subset, if r equals 3, n equals 5, that means we're going through, generating all the subsets of the numbers 1 through 5, right? These are the numbers we're picking from, 1, 2, 3, 4, 5, and we're generating subsets of size 3 from those numbers. All right, so the very first subset is the numbers 1 through r, so 1 through 3. So the very first one is 1, 2, 3, right? And again, there are indices. You can think of them that way. But like that's the first subset. And then I want to send that to next subset. Like I'll output that. Give me the next one. So, all right, we have to play this game. So let k be the largest index such that s of k, the thing there, is less than n minus r plus k. So let's calculate that magic number. What is n minus r plus k for us? All right. So this is important that we start our indices at 1. The algorithm considers these indices starting at 1. That's very important. 0 will throw things off. So like this is index 1, this is index 2, this is index 3, and the values are also the same right now. Okay. So with that in mind, all right, we're trying to look for this number. We're gonna find k being the rightmost thing, the largest index, such that s of k, the thing there, is less than n minus r plus k. So what's n minus r plus k? It's going to be 5 minus 3 plus whatever k was. All right, so let's try all of these. Let's let k be each of them, right? So we want to find the rightmost thing such that this holds for it, right? So at index 1, I see a 1, so k is 1 for that one, so like s of 1. I need to check and make sure that it's less than, going back here, make sure that's less than n minus r plus k. So make sure that's less than 5 minus 3 plus k, which is 1. We start those indices at 1 for this one. So is s1 less than 5 minus 3 plus 1, which is 3? Yeah, 1's less than 3 for sure. So that's good. All right, is that less than 3? Yes. And then we also check, like, tried them all. I want the rightmost one. So is s2, is it less than 5 minus 3 plus 2 now? Because k is 2. That's the index of the 2. So is the thing there, is the 2 less than 4? Yeah, it sure is. And then s3, is that less than 5 minus 3 plus 3 now? I think you can see that's going to be 5. So is 3 less than 5? Yeah, absolutely. And so that's going to be my sk. The rightmost thing such that this kind of expression holds for it, sk. It's really just finding the next thing that could be bigger, the rightmost thing that could be bigger. Okay, that's what it's doing. So we found one, so we're going to increment it. sk equals sk plus 1. Okay, so the 1 and the 2 stick around, and then this one became what it was plus 1. So it becomes 4. We change that. And then everything after it, right, from k plus 1 to r, we also are going to like shift it over and increment. But actually there's nothing after k right now. There's nothing over here. There's nothing after it. So actually we're done. This is the next lexicographic ordering of a subset. So 1, 2, 3 becomes 1, 2, 4. Does that make sense? So I think for the same reason, right, if you run this again, output that one, run next subset on that, you play the same game, and you'll notice like, okay, 4 could still be made bigger, right? We're going up to 5. And so like that's what this kind of comparison is doing. Find the rightmost thing that could be made bigger. So this will get turned into 1, 2, 5. And then also, like everything after that, we do something special, but we still haven't gotten there. Okay? Does that make sense? So that's the goal there. So now we're, that's the next one. 1, 2, 5 is the correct next subset. And then we're going to print that one and give me the next one. See? So what's the next one after that of 1, 2, 5? Again, we want to find the rightmost thing that could be made bigger. Up to 5. You got to be less than an index that is important. So like this one, index 2 better be less than 4. This one better be less than 5, right? So like, all right, this one, is it less than 3? Yes. This one, is it less than 4? Yes. This one, is it less than 5? No. Okay, so the rightmost one now is 2. That's the next one that could be made bigger. It's less than 4 still. That never changes. So this is our sk for this one. See it? And then we finally get to do things. All right, so this will get incremented. So sk equals sk plus 1. Increment it. So this gets turned into 1, 3. And then the things that come after, the way you do it is like, all right, for everything after, the thing that you're going to place there is the thing before it plus 1. All right, so like the thing I put here is the thing before it plus 1, so 4. This becomes 1, 3, 4. You see that? I hope that makes sense. So that's the goal. That's what's going on. And if you just follow this again, like the next one's going to be 1, 3, 5, right? Because this could be made bigger. It's the rightmost thing again. There's nothing after it. 1, 3, 5. You kind of see the ordering going on there. And then now this one, what's the rightmost thing that could be made bigger? 5 is already as big as it can be, but the thing at index 2, that could be made bigger to 4. So sk is again here. And so you're going to advance it, right? We're going to get 1, 3, 4. Or sorry, the 3 becomes a 4, 1, 4. And then everything over here becomes the thing before it plus 1. So 1, 4, 5. Okay, that's going to be the algorithm. And then finally, that's the last one I want to show you as an example. What's the k here? It's like, could this be made bigger? Yeah, it's less than 3. Could this one be made bigger? No, it's already 4. Could this one be made bigger? No, it's already 5. So now it's 1. 1 is our sk. There's my sk. What do I do to it? I increment it, and then the thing that goes here is the thing before it plus 1, so 3. And then again, I have another one to fill in. And it's still, right, it's always the thing that was before it plus 1. So it really just goes 2, 3, 4. It's like the 3 plus 1, that's what's going here. That's our 4. And so that's going to be our next subset. Dot, dot, dot. I think you can kind of understand the game now. All right, so it's going to go forever and ever and ever. And the last subset is n minus r plus 1 all the way to n. So if you think about that long enough, if the size is 3, n minus r plus 1, it's going to be 3, 4, 5, right? That's the biggest one, if you keep that order at least. That's the last one. So the last subset is that one. All right, so it's going to go until then, and that's it. Okay, and so this is another one you'll have to implement. And so like think about how you'll write your loop to like check all these things, find your indices, do these ideas. All right, remember to start it at 1 though. That's important. Start thinking about indices at 1, even though like you're going to be given a vector in C++. And indices start there at 0. You're going to have to do some translation as you're doing your work. All right, that's the next subset. That's a fun one. Let's next talk about binomial coefficients, this is something I had seen before I took my version of this class, so it's probably something you've seen before. Remember binomials, right, from like an algebra class? So b plus o to the 3rd power, for example. We got 2 variables, taking them to the 3rd power. That expands to the following, right? You've got, if you do all the FOIL stuff, it's like b cubed, 3 b's, or b times an o, right? B times O, or B times O times a B, like B times 2 O's. Like you got all the options because it's like there's 3 things being multiplied together. You got all possible options. OBB, OBO. Do you kind of see what's going on here? Interestingly enough. The order doesn't matter, right, of these additions. Like you're just getting a number, right? The answer is this, B cubed plus this fancy stuff. Order doesn't matter, but what does this tell us about subsets? Do you see how it's kind of like, it's giving you things. Like this is every possible permutation where you pick from B and O, right? And you're taking 3 of them. So like you have 2 B's and an O, how many times? You got it once, 2 B's and an O, twice, 2 B's and an O, 3 times. 3 times B squared O. It's like, that's something we can do, right? These coefficients right here, this is a 1, there's a 3 here, another 3 here, 3 of them when you have B and then 2 O's, for example, and then one more, one where there's just 3 O's, okay? That's what it simplifies to, and you can just like figure that out quickly with these numbers, right? You made the Pascal's triangle. So from left to right, they are binomial coefficients of what you see there, and an interesting fact is they are palindromes, like the 1331, like that is the answer for all these things. It reads the same forward and backwards. That's powerful. That's pretty cool, right? So there's a theorem to go along with this. It has to do with the Pascal's triangle that you've maybe seen before, hopefully. The answer is, well, if you're doing this kind of thing, you got a binomial, right? It looks like this. It looks like a plus b to the nth power. The binomial coefficient of this guy, ak times b to the n minus k, because they always add up to 3, right? It's like 3 b's. 2 b's and an o adds up to 3, the exponents. 1 b and 2 o's adds up to 3. 3 o's still adds up to 3. See that? It's always going to add up to 3. So it's like ak times b to the n minus k. It's always going to add up to n, yeah, because that's the exponent. So apparently the binomial coefficient is this, n choose k. Isn't that nice? That's pretty cool, pretty powerful. It's always n choose k, and that is also the same as n choose n minus k, and that's going to give us, like, that's a cool fact that gives us the fact that it is its own little palindrome there, right? And so one way to get it is to do the Pascal's triangle. So I'm sure you've seen this before, right? It's kind of like you start at 1s, like 1 choose 0 and 1 choose 1. Those are 1s. Sometimes you put a 1 above it. It's like you got 1s on the sides always when you need stuff. And like the things that go underneath, right, are, you add them up. The 1 plus 1, that makes 2. All right, that makes 2. And like these are always 1s on the sides, always 1s. So that's one way to calculate things now that we know it lives there. So like there's a 1 plus a 2, so like this must be a 3. If we choose 1 is 3. This is like a 2 plus a 1 again, so this is also 3. So there's my 1, 3, 3, 1 actually. See that? That's kind of cool. So yeah, this was invented by Blaise Pascal. Little chart that tells you, maybe you didn't see this fact before, but it's like, it's a bunch of n choose k's. Like this is 1 choose 0, 1 choose 1, 2 choose 0, 2 choose 1, 2 choose 2. Like that's the order to it all. And that gives us, that leads to this fact. That leads to an identity called Pascal's identity. Okay, so the number of ways to select a set of k items, right? The fact that this plus kind of works out. Like I can't add these and get this. It's kind of cool and recursive almost. The number of ways to select a set of k items from a set of n items, it's equal to the number of ways to select k minus 1 from n minus 1, k minus 1 items from n minus 1 items, plus the number of ways to select k items from n minus 1 items. So that's just the word way of saying this, right? Because this is like, you got n minus 1 items, you're choosing k minus 1. You got n minus 1 items, you're choosing k. You add them up. And apparently, the next thing below it in the triangle is n and k. It's like those are related in a cool way. That's an identity, not equality. Okay? So that's where we get all these things. Just add these up with smaller sets, actually. Smaller sets. We get some fact about bigger sets. That's pretty cool, right? And just the word identity, by the way, is just showing, it just means that it's a theorem that is proving that two things are equal. So we're going to prove that these added together are equal to this. All right? And this is going to be the idea. Let's prove that. Let's prove why Pascal's identity works. Here's the theorem. This is equal to these two things summed together, which is very cool. All right? So here's going to be our proof. What we're going to do is we're going to pretend we're counting k subsets of a set A that has n things in it, all right? Because that's what we're doing, right? N choose k. We're counting k subsets of a set called A. So subsets are size n, or sorry, subsets are size k. There we go. That's the thing on the bottom. And then n is the number of things, thing on the top. Okay? So, for an example, let me just show this to you as an example. This is going to be the proof. Is right there. Let me prove that to you, just for example. Hand wavy for now. Let's say that k is 3 and n is 5. All right? And so that means our full set is the set 1 through 5. So our entire set A is the set 1 through 5. Let me show you how this is kind of working. So the way that this rule works out, the way that you can do this kind of addition, is that you're trying to make k subsets of this guy, subsets of size 3 of this size. One way to break this down is to pick an element and consider all the k subsets with the 5 and all the k subsets without the 5. That's kind of the secret here. Okay, so that's what you do. Just take one and you leave it out. All right, so you try and find what are all the length k subsets that contain. This is the last thing. That's called A sub n. Contain A sub n, and that's I don't know, all the things that contain 5. You got the 1, 2, 5. You've got the 2, 3, 5. Stuff with 5 somewhere. You got the 3, 4, 5. Trying to keep it in lexicographic order, right? So you got a bunch. There's a set of all these possibilities. And do you see how that's completely separate from all the options that don't contain the 5, right? What are all the length k subsets? That don't contain A sub n. Well, you got things without 5. Sorry, you got the 1, 2, 3. You've got 2, 3, 4. You've got 1, 3, 4. You've got many options. And do you see how these are disjoint? There's nothing in here that's in here because there's these ones have 5s, these ones don't have 5s. Does that make sense? So the secret is, all right, how do you count this? We've broken it down. We know that the answer is the size of this set plus the size of this set. What is that size? Well, it's really the number of k subsets that contain the 5. How do we count these? Well, it's just I know I'm putting a 5 in each of these sets. Let me just generate all of the k minus 1 subsets, all the subsets of size 2, because I'll just remember to tack a 5 on. Do you see that? So then we could let's go and generate subsets of size n minus 1, right? Give me subsets of size, subsets of size k minus 1. See that? It's 1 through 2, 2, 3, 3, 4. Things of size 2, right? Because I want to always put the 5 on this side, right? It's just one less thing. And then pick the numbers from 1 through 4, right? Because those are the other numbers. And that's n minus 1 numbers. It's that's how you count how many there are here, right? It's n minus 1 choose k minus 1, because there's a 5 going there for sure, always. So that's that side. And then this side is the number of k subsets that don't contain A sub n. And so it's just you're picking k things still, 3 numbers, but you're picking them without the 5. So it's really only 4 numbers that you're choosing from now on this side. So it's going to be n minus 1 choose k. And that's more or less the proof. All right, you can make that more precise, but that's the secret. You can do math if you need to, but that's the number of k subsets of A, this big number, can be thought about when you're picking from a smaller amount of things, either the same amount or a slightly different amount, one less. All right, but that's our identity, that holds. All right, and that's kind of the proof. And so I want you to try this. So with this in mind, really you're just going to use this idea. You can draw out the triangle if you need to, but this is the binomial theorem. This is the one you need right now. Let's say that we're taking these two numbers, right, 3x minus 4y, to the 8th power. There's going to be a term, right, because the x's and the y's will always add up to 8. There's going to be an x to the 5th times y to the 3rd term. Okay? And what is the thing that's going to be out in front of it, is my question to you, because you got 3's and 4's now. You got some coefficients. You see that? So really, binomial coefficients, you got your a plus b to the n. What is a and what is b in this example? A is 3x, right? That's supposed to be plus b, so the b is negative 4y, right? And it's to the nth power, so n is 8. And so see if you can figure this out using the formula. And the same for this one. Do them both, please. All right, for this one at least, we want x to the 5th, y to the 3rd term. So like, there's one more thing involved here. It's like there's a k. Right? The first one doesn't have to be, the order doesn't matter because either way goes. Let's just consider the first one, that's what k is. Okay? So let's say that k then is 5. That's just the first term. That's that exponent. So let's consider k to be 5. You could totally have considered k to be 3 because it is fine. Right? It works the same way. So let me show that to you. So what's the term? It's going to be right. It's going to look like x to the 5th, y to the 3rd, times some weird looking stuff, right? It's going to be, what's the binomial coefficient? It's going to be n choose k, or equivalently n choose n minus k. Either one you want to do. So n choose k is 8 choose 5 for this example. So that's the coefficient, but we're not done, right? Because we had 3's and 4's, 3 here and a negative 4 actually. And so every time we take an x, we're multiplying it by a 3 still. Yeah, and every time you multiply a y, you're taking the minus 4 again, right? You're taking those powers. And so every time an x got brought along, you brought the 3 there with it. So there's more here, right? There's a 3 to the 5th. And then there's also, every time you brought a y into the game, you brought a negative 4 with it. So there's 3 y's. So you're going to take negative 4 to the 3rd power. There's that. And then that's times this. This is just how many times you're going to double count the rest of this. Okay, that's the idea. But this is the full coefficient, and so that's something you have to worry about. Okay, and then for this one, and then you can do the full math if you need to. Let's talk about this one. So x to the 6th, y to the 1st in terms of this one. So it's going to look like x 6 y 1, and then just quickly, right? It's going to be, all right, there's 7 here. That's our n, and let's consider k to be 6. So 7 choose 6. And then every time we took an x along for the ride, and there's 6 of them, we got a negative 2. So it's negative 2 to the 6th power. That's part of the coefficient. And then negative 5 to the 1st power. So this, whatever this is, that's your full answer. That's your coefficient in front of that. Okay? So that's the game you play there, and I hope that makes a little bit of sense. Okay? So yeah, the last topic I want to tell you about today is called the pigeonhole principle. It's very simple, surprisingly. It gives you a lot. It's very powerful. It's a really nice tool to have. It's a simple idea that leads to some very easy proofs, okay, of hard things. So the pigeonhole principle, it's a silly idea. It's like, consider pigeons. They're trying to fight over places to have their nest or something. They're pigeonholes. So let's say if we have n plus 1 pigeons, and we're trying to place them into n boxes. You know that n plus 1 pigeons have nested in n pigeonholes, then there's more pigeons than holes, right? There must be at least one box then, in the best case, with more than one pigeon. Sure, they can all be having a party, right? Let's pretend. All right? This is a very simple idea, right? So simple, yet it's very, very useful. It's like here's the idea. Let's prove it. I'll prove it by contradiction in a second. Let's say that like you've got, I don't know, you've got 8 pigeonholes, and you know you have 9 pigeons this is true about them, right? There must be at least one box with more than one pigeon. They could all be having a party. They could all be in one box. That's fine. All 9 of them could be there. But in the best case, where there's as they're spread out as possible, as humanly possible, you try to put one here, all right, one here, 3, 4, 5, 6, 7, 8. You spread it out as much as possible, but you know there's 9 pigeons and 8 boxes. There must be at least one box where there's 2. See that? That is, it's very simple, but it leads to some very easy proofs. It's very cool. So let's prove this by contradiction. Okay, so assume, right? Assume this is not true. There must be at least one box with more than one pigeon. Assume that's not true. Assume that every box has, assume each box, we've kind of done a problem similar to this before. We just haven't heard the term yet. Assume each box has, well, for the sake of contradiction, if it's not more than, at least more than one, that must mean that every box, right, has less than or equal to one pigeon in it. Less than or equal to one pigeon. Okay, so then what do we know then? What do we know? Then there's n boxes, right? And each box has a less than or equal to one pigeon. Then the number of pigeons because the boxes could be empty. Max the number of pigeons is less than or equal to 1 times n. But we have n plus 1. But n plus 1, which is as many pigeons as we know we have, that's strictly bigger than n. Contradiction. QED. So that's the pigeonhole principle. It's very simple, right? Formally, somebody does a real proof of this. It's formally defined using functions and the size of the domain and codomain. So it's like, this is your domain of size 4. If you have a codomain of size 3, like this could never be 1 to 1. Yeah? So like, you can pick a place for that one, and spread it out. You can pick a place for this input to that output, pick a place for that input to that output. And then this output, you have to put somewhere. It's forced to pick one of the ones you've already picked. So it can't be 1 to 1. See that? That's the idea. So that's how it's formally proved, but we don't have to care about that. We're gonna use the idea. Use the pigeonhole principle. So here's how you use it. Here's some cool examples that are kind of fun word problems for once. So let's pretend we have a drawer of 3 different kinds of socks, all right? And we're very lazy and we don't fold our socks. So none of them are in pairs right now. You put a blindfold on, you take a sock out, it's just a single sock, all right? So in the worst case, this is the pigeonhole principle at play. You are forced to take out 4 socks if you put on a blindfold. You're forced to take out at least 4 socks, right? You have to take 4 socks out until you can find a matching pair, in the worst case, okay? Sorry, I said the word at least, but I shouldn't have. In the worst case, you have to take out 4 socks to get a matching pair, right? In the best case, you take out 2 socks and they're both the same kind, right? Because, like, here is the worst case, right? You take out, like here's your drawer. You got sock 1, sock 2, sock 1. They're all separate. Sock 3, 3 different kinds of socks. Sock 3, sock 2, and you go in blindly. Like you could totally in your first 2 draws take out 2 of the same kind of sock. That's totally possible. But in the worst case, you take one of sock 1, then the next one you take is sock 2. Oh no, they don't match. The next one you take is a sock 3. Oh no, they still don't match. Nothing matches. Do you see how the next time you take a sock, it's gonna be one of 1, 2, or 3. It's gonna be either this one, right, or this one maybe, or this one. Either time, you now have a pair. But in the worst case, you had 4 things, right? So you try to spread out as much as possible. Like in the worst case, you have the worst luck. The first sock you take is sock 1. The next sock you take is sock 2. The next sock you take is sock 3. Now finally, you're going to get one of those. Like maybe it's S1 again. It's always going to be. In the worst case, you have to wait till the 4th one, right? Here's the coolest example, one of the coolest examples in the class, I think. It's a fun idea. So this is a true statement I'm about to tell you. There are 3, all right? There exist at least 3. There exist 3 non-bald people in Fresno with the exact same number of hairs on their head. That's a really cool idea, isn't it? It's a really weird thing to claim, but it is absolutely true, beyond a shadow of a doubt. Let me tell it to you, using the pigeonhole principle. Here's what we know. The number of hairs on a person's head is strictly less than or equal to 200,000. That's like the upper limit of hairs a person can have on their head. And Fresno has a population of more than 500,000, all right? So in the worst case, like you're trying to spread out how many hairs each number of people has, like a baby has 1 hair, another baby has 2 hairs, 3, 4, like you try to put everybody into one box. Like there's only one person with 1,000 hairs. There's only one person with 2,000 hairs. You try to spread it out as much as possible. Well, once you get to box 2,000, you're trying to spread it out. You have to start repeating. Boop. See how there's overlap, even if you're trying to spread it out. And again, you go another 2,000, so that's 4,000 total. You're still trying to spread it out as much as possible. You get to the 4,001th box. At a minimum, you're going to have to put 3 things in it. You see that? That's the goal. And then, of course, there's more than that. But that is the proof, right? The idea, this is true because, like, even if you're trying to spread it out as much as possible, 5,000 things, 5,000 people, over 2,000 possible hair combinations, amounts of hair, that's bigger than 2. See that? The fancy way to say that is like the 500,000. The reason this is true is the ratio of people to hairs in somebody's head. You take the ceiling of that, that's equal to 3, right? So there has to be at least one pigeonhole with at least 3 pigeons. You see that? One number of hairs, whatever it is, I don't know, maybe it's 187,000 hairs. There's at least one amount of hairs that 3 people share that amount. See that? Even if you're trying to spread it out as much as possible, you're forced, just because of the population, to have at least 3 people in one of those boxes. Isn't that cool? That's so cool to me. Okay? There's some cool examples that we can think about here too. So here's another example. Let's say that we pick 5 cards from a deck, all right? At least 2 of those cards then, it's like the sock game all over again, at least 2 at that point, maybe more, but at least 2 must have the same suit at that point, because there's only 4 suits in a deck, right? Maybe the first card you draw is clubs, then the next one is spades, you're getting unlucky, then hearts, then diamonds. Like in the worst case, you're drawing 4 of each of the different ones, and then the 5th one, right? You gotta draw 1, 2, 3, 4, and then the 5th one is finally, it's forced to be one of the other 4, right? So maybe you draw a heart next. So you gotta wait, in the worst case, until 5 cards to get 2 of the same suit. Okay, that's just, it's so logical, but now we're spelling it out. It's called the pigeonhole principle. All right, here's another one. Let's say that we're going to pick 10 arbitrary 2-digit numbers. This is another surprising one. Right? Pick 10 arbitrary 2-digit numbers. Just like, all right, just think of them. Make a list of 10 arbitrary 2-digit numbers. All right, it's okay if they have zeros in them. There are 2 subsets of those numbers. I don't know which ones they are, but there's at least 2 subsets of those numbers of some amount, maybe 5 of them, like a group of 5 and a group of 3 or something. Don't have to be the same size either. There are 2 subsets of those numbers, though, that are different, that have the same sum. That's really cool, all right? So it's like, I don't know, generate, right? The reason this works is, let's see, how do I want to explain it? Like you pick your numbers, like you pick your random 10 numbers, like maybe there's 15 and 21 and like 33 and 87. There are, like this proof is saying, like there are some subsets of those 10 numbers, maybe this one and this one, that add together to be the same amount, all right? And the reason this works is because like you're going to run out of options, even in the worst case, all right? So the secret is the number of possible subsets of 10 numbers is 2 to the 10th power, right? It's just like you take everything or you take nothing, right? For each option. So 2 to the 10th power, that's the number of possible subsets of 10 numbers. That's how many there are. And that is strictly bigger, right? That is strictly bigger than this, the number of possible sums, right? Of 10 numbers, right? Because like, that's the secret, right? Because the set of possible sums is like, you add up all the zeros, like maybe you choose 0 10 times. Like that's the smallest sum. The next bigger sum is 1 all the way to like maybe your numbers were 10 99s. See that? So the set of possible sums, the biggest sum is 990. Do you see that? So the set of possible sums is 0 all the way through 990. That's like the largest sum of 10 two-digit numbers. You could have picked, in the worst case, 10 zeros, right? That would give you a subset of size sum 0, all subsets of sum 0. Or you could have picked, right, subsets of sum of 99, size 99. And that's like the largest sum that you could possibly make, 10 99s. And so the number of sums is smaller than the number of subsets, and so that means at least two of these subsets, because there's going to be at least one overlap if you try to spread it out, at least two of those subsets, right, will have the same sum. Maybe more, but because of this ratio, it's bigger. This is bigger. There's more subsets than possible sums, so some of those subsets better share a sum. Or some of those sums better share a subset is probably the better way to say it. Do you see it? Write it out. It's very, very cool, very powerful. So that's the pigeonhole principle. Your turn. Here's some questions for you. Give them all a try. They're going to be pigeonhole principle stuff, but see if you can do them all, and then I'll show you all the answers. So for the first question, how many people must be selected to make sure there are at least 20 who are born in the same month? Let's figure this out together. So in the worst case, like you're trying to select people, you get really unlucky. You want 20 born in the same month. There are 12 different months, right? In the worst case, you pick 12 people and they're all from different months. That sucks. 4, 5, 6, 7, 8, 9, 10, 11, 12. So in the worst case, like you draw 12 people and they're all different months. Okay? You want 20 in the same month. So the second you draw the 13th person, there's going to be an overlap somewhere. So if you want to spread it out, in the worst case, right, you have as few number of people born in the same month as possible. And so you just want to do this a bunch of times. Another 12 people. In the worst case, you've 36 people. At most, you have 3 months in common among a group of them. So you want to just keep on playing this game. It's like, all right, how many times do you have to do this? In the worst case. In the worst case, you've taken 12 people 19 times, right? You've drawn this out 19 times. In the worst case, right, they're all spread out evenly, and they're all sharing 19 birthdays per month. The second you add one more person, right, in the worst case, this is all spread out, there's 19 people in each month, you'll force one more person that will force upon you a 20th person in one of those months, okay? That's the secret. That's the idea. So, yeah, what we're searching for is, like, in the worst case, like we're trying to solve something. Like we're trying to solve, like, if we spread it out, right, some number n over 20, when we take the ceiling of that, when is that bigger than or equal to 20? Okay? In the worst case, right, you've chosen 19 times 12 people. Still over 12, right? You spread them out. The ceiling of that is still only 19, right? Because you chop off the 12s there. The second you add one more, though, that bends it in your favor, and that gives you a 20th person in at least one of the months. Okay? You see that? That's the secret. That's how I want you to think about it. Okay? Here's another question for you. At least how many people in a group of 50 were born in July? So you got 50 people. At least how many were born in July? Can you use the pigeonhole principle to find that? You can't. You see how that's a trick question? Trick question. There is no answer. You see it? Think about it. What if they're all born in January? You could find a group of 50 people born all in January. That's very easy to find. There is no answer. It's a bad question. It's a trick question. Do you see how you have no control over who's born in July? All right? You have control over, like, overlaps and things. That's what the pigeonhole gives you. Pigeonhole principle gives you. It gives you control over overlaps. It can give you answers about overlaps, not about some arbitrary thing. Okay? So for the last question, this is a real one. Now, it's not a trick question anymore, but it's a harder one maybe. More ideas. So the population of California, at least the last time I checked, was like 40 million. I'm sure it's more now, but let's pretend it's 40 million people. The question is, at least how many people have the same 3 initials? Okay? Assume for the sake of math that everybody has a middle name. So everybody has 3 initials in the state of California. All right? So how many options are there for initials then? Because this is a question now also about permutations in a sense, or really it's just the product rule. So you have 26 letters in the alphabet. If you have any combination of 3 of them, like you want to count every combination of 3 of them, you can go all the way from initials AAA, right, to initial AAB, to initial ZZZ. So it's 26 cubed possibilities for initials. And so we have 40 million people in the state of California. And so in the worst case, you want to spread them all out into each possible of the 26 to the 3rd power options for middle initials, or full initials, sorry. So you want to spread that out. This is your option. That's what you're going to get. That's your ratio. And so, like in the worst case, like you give as few as people as possible AAA, as few as people as possible AAB, all the way to ZZZ. What do we get when we add it up, right? That's going to be the ceiling of all this. And so that's going to be our answer. Whatever is that. Whatever this is, like this is the ratio of like spreading them out as much as possible. Taking the ceiling is going to tell you there is at least one group with that many, maybe more, in the worst case. Okay, so let's do that. I can do that in Python. So that's 40 million over 26 to the third power. And if we ceiling that, I think I might have said floor before, sorry, it's ceiling. You round it up, so it's 2,276 at least people have the same three initials. I think you can imagine there's a lot of like John Smiths in California, John something Smith, I don't know. So there's probably plenty more, right? This is a lower bound, probably plenty more than 2,276, but that's your minimum, all right? At least this must be true, all right? Based on the pigeonhole principle. It's a cool little idea, I think, all right? So that is what I wanted to say about that. It's a really cool idea. It's a nice, simple one, but it gives you a lot of power when you're doing problems. So that it's a good one to end on for our counting slides. So I'll see you back here with some new slides next time.